In this video, we'll take a look at finding integrals using something called U substitution. So we're going to integrate the following function. The integral of x to the third minus 2 to the power of 6 times 3x squared dx. So before we do that, I'm going to remind you of something from derivatives, the chain rule. Because what we'll be doing is basically the chain rule backwards. So remember that if you have a function, f of x, is equal to parentheses, I'll use 3x squared minus 1 to the power of 4. We use the power rule, but we also have, notice we're taking the derivative of 3x squared minus 1 to a power, not just x to a power. So when we took the derivative with the chain rule, we applied the power rule to the outside function, 4 times 3x squared minus 1 to the power of 3, that applies the power rule, times the derivative of the inside. The derivative of the inside of 3x squared is 2 times 3 is 6x, and the derivative of 1 is 0. So we ended up with a derivative of, in this case, 24x times 3x squared minus 1 cubed. So what we're doing now, if we're taking the integral, that means we have the derivative and we're working backwards. So take a look at what we have. We only have the power rule for integration right now. So if we're going the opposite direction on power rule, integrating instead of derivative, the integral of u to the power of n du is equal to add 1 to the power u to the n plus 1 divided by n plus 1 plus the constant. So we have to figure out how we're going to apply the power rule in integrals that use the chain rule. So it's a method called U substitution. So this method of U substitution is a method of integration that essentially involves using the chain rule in reverse. And it's used when we have a function that's actually a composition of functions. So here's how the process works. We want to find the integral of x to the third minus 2 to the power of 6. Notice we have a function inside of another function. The function x to the third minus 2 is inside another function u to the sixth. So if you think of the composition of functions, f composed with g of x, it's x to the third minus 2 to the power of 6. So what we're going to do using a u substitution is we're going to let u, the variable u, equal the entire expression x to the third minus 2. Then we find the derivative of u with respect to x. So du dx is equal to 3x squared, and then the derivative of 2 drops off. Then solve for du. Think about it as a fraction, du divided by dx. Multiply both sides by dx. We get du is equal to 3x squared times dx. Now, u is equal to x to the third minus 2. Du is equal to 3x squared dx. Notice in my integral, I have x to the third minus 2 to the sixth times 3x squared dx. My du is 3x squared dx. So now this is where substitution comes in. Substitute the expressions in step 1 and 2 into the original integral. So now our integral is going to be x to the third minus 2 is going to be substituted with a u. And now I have u to the power of 6. 3x squared dx is going to be substituted with the expression du. So what I did was just rewrote the integral in terms of a new variable u that represents the expression. And now I can use the power rule backwards to find the integral. So the integral of u to the sixth du is u to the power of 6 plus 1 divided by 6 plus 1 plus the arbitrary constant c. So I get 1/7 u to the 7th plus c. And now I can substitute what the expression I used for u back in, and I end up with 1/7 times the expression I used for u, let me go back up here, u is equal to x to the third minus 2. So I'm going to substitute x to the third minus 2 back in to the 7th plus c. So this is my integral. How do you check and make sure? Check by finding the derivative. So if I find the derivative of 1/7 times x to the third minus 2 to the 7th, I've got to use the chain rule. Keep the 1/7 times, apply the power rule to x to the third minus 2 to the 7th. I get 7 times x to the third minus 2 to the power of 6 times the derivative of the inside. The derivative of x to the third minus 2 is 3x squared. The derivative of the arbitrary constant is 0. So now when we do our arithmetic work, 1/7 times 7 cancel each other out, and I'm left with x to the third minus 2 to the power of 6 times 3x squared. And if you take a look, that's what my original function was that I'm finding the integral of. So that's my original expression. So it's the chain rule backwards by using something called a u substitution. All right, so here's some practice problems. And how do you know what to let u equal? Okay, so I have whatever is in parentheses, the expression to the power, is what you let u equal. So in this case, the 1 minus 2x is going to be what I let u equal. Then find du dx, the derivative of u with respect to x. So find the derivative of your expression. Derivative of 1 is 0. Derivative of negative 2x is negative 2. Then solve for du, multiply both sides by dx. Du equals negative 2 dx. Now substitute. This expression du has to match this expression negative 2 dx exactly. So in this case it does. If it doesn't match it exactly, it can be off by a multiple of a constant. Okay, but in this case it matches exactly. So now substitute. I get the integral of, instead of 1 minus 2x, I'm going to put in u to the power of a third, and then substitute negative 2 dx with your expression du. So the goal is to substitute so that you can use the power rule backwards. So now the integral of u to the 1/3 du is going to be u to the 1/3 plus 1 over 1/3 plus 1 plus the arbitrary constant. 1/3 plus 1, 1/3 plus 3/3 is 4/3. So I get u to the 4/3 over 4/3 plus the arbitrary constant. Now last arithmetic step, dividing by 4/3 is the same as multiplying by 3/4. U to the 4/3 plus c. Once your integral is simplified, then take what you let u equal at the beginning and substitute it back in. So my answer now is 3/4 times 1 minus 2x to the power of 4/3 plus the arbitrary constant c. All right, we'll take a look. That's a couple of cases where when you find the derivative of u, you get exactly the same value, same expression, and can substitute it directly. So now let's look at an example. What if that doesn't exactly match up? Okay. So next example, we're going to take the integral of 2x plus 6 to the 5th dx. So we're going to let u equal the expression that's being raised to a power. So u is equal to 2x plus 6. Then take the derivative of u with respect to x. I end up with 2, and then multiply both sides by dx. Du is equal to 2 times dx. So notice this du equals 2 dx, and I have a single dx. So these expressions have to match exactly. So it'll be some multiple of du that you can substitute. So to have the expressions match exactly, instead of 2 dx, I need a single just dx. Divide both sides by 2 or multiply both sides by a half. I get 1/2 du is equal to dx. So now I have exactly dx, and I can it as an expression of du, and I can substitute that in. So in the substitution, the integral of 2x plus 6 to the fifth is now u to the fifth times dx. dx is equal to 1/2 du. So you can rearrange this, rewrite the 1/2 times u to the fifth du, so it's written in a little bit more familiar way. And now you can take the integral, use the property. So now we have 1/2 times u to the fifth, 5 plus 1 would be u to the sixth divided by 6, plus the arbitrary constant. That would give us 1/12 times u to the sixth plus c. Then substitute the very last step, substitute back in what you let u equal in the first place. So our final answer is going to be 1/12 times 2x plus 6 to the power of 6 plus the arbitrary constant. All right, let's try another one. Let's go ahead and look at C. We have the integral of, get a little bit of room, x squared times x to the third plus 1 to the power of 3/4. If you want to rewrite the original problem so that you have the expression raised to a power first, x to the third plus 1 to the 3/4, and then the x squared dx is written after it, okay, so that you can tell on your u substitution if you've got everything you need. So we let u equal whatever's in parentheses to a power, x to the third plus 1. Take du dx and solve for du. We're going to get the derivative of x to the third is 3x squared times dx. And then you check. I've got x squared dx times 3. I need x squared dx. These have to be exactly the same. So multiply both sides by a third or divide by 3. I get 1/3 du is equal to x squared dx, which now they're exactly the same. So I can substitute an expression in terms of du. So now I'm going to do the u substitution. I'll get the integral of u to the power of 3/4 times 1/3 du. Do a little rearranging by rewriting the 1/3 times u to the 3/4 du. And now you can apply the power rule. So all this work is done up front before we even do the calculus portion. Take the integral, I get 1/3 times u to the 3/4 plus 1 over 3/4 plus 1 plus the arbitrary constant. That's 1/3 times 3/4 plus 1 would be 3/4 plus 4 over 4 is u to the 7/4 over 7/4 plus the arbitrary constant. Simplify our expression. U to the 7/4 divided by 7/4 is the same thing as times 4/7. And I end up with 4 over 21 times u to the 7/4 plus the arbitrary constant. And the very last part is substitute for u the x to the third plus 1 from the original expression. So I get 4 over 21 times x to the third plus 1 to the 7/4 plus the arbitrary constant. All right, so it's a lot of work, but so keep track of what you're doing. But that is how to do the chain rule backwards. Let me help you with B and D, just setting up your integral, and then you follow the same process. So for part B, get a different color here. So for question B, when you write the integral, write that t squared plus 8 instead of as a root, write t squared plus 8 to the power of a half times 3t dt. And then you'll go from there. Then part D, oh, that's okay. Well, that one would be worth finishing actually. So let u equal t squared plus 8. Then du would equal 2 times t dt. Okay, so I get 2 times t dt, but I want 3 times t dt. So what do you have to multiply 3 by, or 2 by, to get 3? So you have to multiply both sides by 3 halves. In order to get, so I have 3 halves du is equal to 3t dt. And now when you do your u substitution, you'll have the integral of u to the 1/2 times 3 halves du, and then go from there. That was a little trickier. All right, part D, to rewrite, part D, you'll rewrite this as the integral of, we can't have a fraction, so think of this entire bottom expression, y to the 5th plus 1. To move it up to the numerator, that's going to be y to the 5th plus 1 to the power of -1 times 2y to the 4th dy. So that's, then you can go from there. The other two, let's see, part E, question E will be the integral of y to the 3rd plus 5 to the -2 times y squared dy to get it in the right form. And I think the others, 34, F and 32, rewrite so that you have the expression to the power written first and then times t dt after. And then 34, bring the square root of 2x cubed plus 1 from the denominator up to the numerator. So that's going to be 2x cubed plus 1 to the power of -1/2 times 2x squared dx.